Ancient artisans mastered material secrets we are still struggling to replicate. This is the true story of how early experiments with fire and stone laid the foundation for our modern engineered world. By the end of our journey, you will see the entire history of technology in a completely new light. We will uncover how a Roman harbor concrete grows stronger after 2,000 years in seawater, and why a Mayan blue pigment refuses to fade after 10 centuries. These are not isolated mysteries but pieces of a larger puzzle about human ingenuity. What does our most advanced material science still have to learn from the distant past around that flickering primordial flame? Our ancestors did more than chase away the dark. They built the world's first laboratory. This was the dawn of pyrotechnology, a profound moment when fire transformed from a source of warmth into a tool for transformation. The earliest material scientists were not wearing lab coats, they were huddled near hearths, and their first great discovery was likely an accident. A lump of wet clay, perhaps fallen or placed near the embers, did not turn to dust. It hardened, it became permanent. This was the birth of ceramic, a material that simply did not exist in the natural world. We find powerful evidence of this at places like Dolní Věstonice in the Czech Republic. There, archaeologists uncovered small, carefully shaped figurines of animals and people, crafted nearly 29,000 years ago. These are not just ancient art, they are data points. They prove that early humans had moved beyond chance encounters with fired clay. They were intentionally gathering specific soils, molding them with purpose, and then subjecting them to controlled heat. They were running experiments. Materials archaeologist Dr. Sarah Johnson explains that these early artisans were unknowingly establishing the fundamental rules of thermal transformation. They learned that different clays required different temperatures, that heating too quickly would make an object crack, and that the resulting material was not just hard, but also resistant to water and decay. This was a monumental leap in human cognition. It was the realization that the application of energy could fundamentally and permanently alter the properties of a substance. This foundational relationship with fire set a pattern that would echo for thousands of years. The principles learned from baking clay, the careful control of temperature and atmosphere, became the essential knowledge needed to later smelt copper from rock, to create the first beads of glass from sand and ash. Every metal sword, every glass vessel, every porcelain cup owes its existence to those first curious individuals who looked at a fire and saw not just a tool for survival, but a gateway to creation. The crucible was born in the campfire, and with it, humanity took its first deliberate step toward engineering the world around it. That first hardened lump of clay sparked a revolution that would reshape civilization itself. In the quiet darkness of places like Xianrendong Cave in China, nearly 20,000 years ago, individuals were not just making things, they were conducting the world's first systematic material experiments. They gathered specific clays, mixed them with crushed shells or sand, and carefully controlled the heat in simple pit kilns. This was not random tinkering. It was deliberate engineering, as they discovered that different mineral additives called temper could prevent their pots from cracking during firing. They were learning to create composite materials, a principle that remains fundamental to everything from modern concrete to carbon fiber. Materials scientist Professor Kenji Yamamoto points out that these ancient artisans were mastering concepts like sintering, where heat fuses particles without melting them completely. They learned through trial and error how thermal expansion worked, ensuring their vessels could withstand repeated heating and cooling over cooking fires. Then came another accidental breakthrough. A pot placed in a certain position within a wood-burning kiln might emerge with a thin, glossy coating. Wood ash settling on the hot clay surface had chemically fused with it to create the very first glaze. This was the birth of engineered surface coatings, a discovery that provided both corrosion resistance and beauty. These early potters across cultures from Mesopotamia to the Americas were building a foundational knowledge of material processing. They established the core principles of controlling composition, temperature, and atmosphere. Every technique they perfected, every thermal transformation they observed, created the essential toolkit that would one day allow humanity to extract metal from stone. The crucible for smelting copper was, in essence, just a highly refined ceramic pot. The revolution began not with a bang, but with the quiet, patient firing of clay. Around 5,000 years before our era, a profound shift occurred in human workshops. The mastery of fire had unlocked ceramics, but now it was about to unlock something far more transformative: metal. The journey began with native copper, a soft, malleable metal that could be found in its pure form and hammered into simple shapes. But the real breakthrough came when some curious individual placed a piece of colorful, metallic-looking rock into a hot ceramic furnace. This was not native copper, it was copper ore, and the intense heat of the kiln did something miraculous. It drove out the non-metallic elements, leaving behind a pool of pure, liquid copper. This process, smelting, was humanity's first great chemical extraction. Archaeologists at sites belonging to the Vinca culture have uncovered the remains of these early furnaces. The evidence is compelling: piles of slag, the stony waste left over from smelting, and crucibles with traces of different ore combinations. These were not single attempts. They represent systematic testing, a deliberate effort to see what would happen if you mixed this green malachite ore with that black arsenopyrite rock. Metallurgist Dr. Elena Rodriguez explains that these ancient artisans were, without knowing the chemistry, mapping out the very first phase diagrams. They discovered that by adding certain minerals to the copper ore during smelting, they could create a new material entirely, an alloy. The first alloys were likely copper mixed with arsenic, which produced a metal that was significantly harder and easier to cast into molds than pure copper. But arsenic is toxic, and the discovery probably came at a great cost. This likely spurred the search for a safer, superior alternative, which they found in tin. The deliberate combination of copper and tin created bronze, a material so revolutionary it named an age. This was the ultimate expression of early material science, the understanding that you could control the very composition of a material to engineer its properties. You could make it harder, more durable, or more fluid for casting. This principle of intentional alloying, discovered through millennia of dangerous experimentation, is the exact same principle used today to create the super alloys in jet engines or the specialized steels in our skyscrapers. The Bronze Age was not just about better tools and weapons. It was the birth of compositional design, a concept that would eventually make every complex technology possible. The mastery of bronze was a monumental achievement, yet the next great leap in material science would emerge from an even more stubborn and abundant ore. Deep within the bloomery furnaces of the early Iron Age, a new kind of alchemy was taking place. Picture a blacksmith, their face lit by the intense glow of a furnace, tirelessly working a set of bellows. They were not just melting metal, they were learning to breathe new properties into iron itself. The critical discovery was carbon. These early metallurgists, working between 1200 and 500 before the Common Era, gradually realized that how long they heated the iron in a charcoal fire and what they did to it afterward could transform the soft, spongy metal into something vastly stronger. The process was called carburization, where carbon atoms from the charcoal would diffuse into the surface of the iron, fundamentally changing its crystalline structure. At sites like Tel Hammam in Jordan, archaeologists have uncovered the remains of these early production facilities. The evidence is not just simple forges, but complex workshops with multiple furnaces and slag pits, indicating a sophisticated, systematic approach to experimentation. Materials historian Professor Michael Chen describes how these ancient smiths were essentially running a continuous research and development program. Through relentless trial and error, they discovered that if you heated a piece of iron in a carbon-rich environment for just the right amount of time, you could create a thin layer of steel on its surface, perfect for a cutting edge. But their innovations did not stop there. They developed quenching, the process of rapidly cooling the red-hot steel by plunging it into water or oil. This sudden cooling locked the carbon atoms in place, creating an incredibly hard but brittle material. Then came the final masterstroke, tempering. They learned to gently reheat the quenched steel to a lower temperature, relieving the internal stresses and restoring some toughness to prevent it from shattering. This trilogy of processes, carburizing, quenching, and tempering, established the foundational principles of heat treatment that are still used in every modern steel mill today. These Iron Age artisans were not just making tools, they were optimizing material properties. They created different grades of steel for specific applications, a harder, more brittle steel for a sword that needed to hold a razor edge, and a tougher, more flexible steel for an axe head that had to withstand repeated impact. This represented the dawn of material selection, the understanding that you could engineer a substance to meet precise performance requirements. The knowledge forged in those ancient fires, the systematic control of carbon content and thermal cycles, would become the essential bedrock for everything that followed, from the layered steel of a medieval knight's sword to the massive I-beams that frame our modern cities. While the Iron Age smiths were mastering the transformation of metals, an entirely different material revolution was brewing in the Roman world. Across the vast empire, from the shores of Italy to the coast of North Africa, engineers were perfecting a substance so durable it defies modern understanding. They mixed slaked lime with a special volcanic ash from Pozzuoli, added chunks of rock, and then used seawater to bind it all together. The result was not just concrete, but a kind of architectural life form. It did not merely resist the sea, it embraced it, growing harder with each passing century. Modern analysis of these ancient harbor walls reveals a secret that was lost for over a millennium. Civil engineering professor Dr. Maria Schmidt explains that the Romans were unknowingly creating complex calcium-aluminum silicate hydrate compounds. The volcanic ash, a pozzolanic material, reacted chemically with the lime and seawater to form a crystalline structure that is incredibly dense and resistant to cracking. But the true marvel lies in its self-healing properties. When tiny cracks do begin to form, seawater seeping in reacts with the volcanic glass and lime to create new mineral growths that seamlessly fill the gaps. This is a material that actively repairs itself, a capability our own modern Portland cement concretes lack. The Roman understanding that specific volcanic materials could create hydraulic cements capable of setting and hardening underwater represented a pinnacle of ancient material science. It was not a single recipe, but a principle of composite material design. They experimented with different volcanic ashes, with crushed brick or pottery, constantly refining their mixes for different applications. The Pantheon's magnificent dome, still the world's largest unreinforced concrete dome nearly 2,000 years after it was built, stands as a silent testament to their mastery. These formulations established principles of durability and composite design that would be lost and then painstakingly rediscovered centuries later. How did this profound knowledge, this recipe for near-eternal stone, simply vanish from the world for so long? Centuries after Roman concrete set the standard for endurance, another material mystery was being forged in the crucibles of India and the Middle East. This was wootz steel, the legendary material that would become known as Damascus steel. Medieval swordsmiths were not just crafting weapons, they were creating a perfect fusion of art and science. The blades they produced shimmered with flowing, watery patterns, a mesmerizing visual signature that hinted at an incredibly complex internal architecture. These patterns were not merely etched onto the surface, they were the visible manifestation of the steel's very soul, a map of its nanostructured core. The process began with a specific type of iron ore mined from India's Deccan Plateau. This ore contained just the right trace elements like vanadium that were crucial to the final result. Artisans would smelt this ore in small, sealed crucibles, carefully controlling the carbon content by adding organic materials like wood or leaves. This slow, meticulous process produced a small ingot of high-carbon steel, a material known as wootz. But the true magic happened next in the hands of the master smith. They would subject the hard, brittle wootz ingot to a precise and secretive regimen of thermal cycling. The steel was heated to a specific, critical temperature, not quite hot enough to melt but just enough to make it malleable. It was then hammered, folded, and drawn out, a cycle repeated dozens of times. This was not random hammering, it was a form of extreme material conditioning. The smiths were using heat and force to manipulate the steel's microstructure on a scale invisible to the naked eye. They were, in effect, performing ancient nanotechnology. Modern materials scientist Dr. James Wilson explains how recent analysis using high-powered electron microscopes has uncovered the secret. These ancient blades contain incredibly fine, aligned structures of cementite, an extremely hard form of iron carbide. These appear as nanowires, thread-like formations that weave through a softer, more flexible steel matrix. This composite nanostructure is what gave Damascus steel its legendary properties. The hard nanowires provided exceptional strength and a razor-sharp edge, while the surrounding softer steel granted the blade a surprising resilience, preventing it from shattering upon impact. It was a material that seemed to defy the usual trade-off between hardness and toughness. The beautiful watering pattern was the visible evidence of these aligned carbide bands, revealed when the finished blade was polished and lightly etched with acid. The loss of this art around the 18th century is one of history's great technological mysteries, possibly linked to the depletion of the specific ores or the breakdown of the guilds that guarded the knowledge. The story of Damascus steel is a powerful reminder that ancient material experiments achieved a level of sophistication we are only now beginning to decode with our most advanced tools. These artisans established the foundational principle of microstructure control, proving that the true power of a material lies not just in its composition, but in the hidden architecture within. The shimmering translucence of glass first emerged from the most ordinary of moments. According to legend, Phoenician merchants were camped on a sandy riverbank, using blocks of natron, a natural salt, to support their cooking pots over a fire. As the fire died down, they noticed something strange in the ashes. The intense heat had fused the natron with the silica in the sand, creating a hard, lustrous substance that was neither stone nor ceramic. This accidental discovery around 3,500 years before the Common Era launched a technological journey that would span millennia. Initially, these early artisans created simple, opaque beads and amulets, but they quickly began to experiment. They discovered that by varying the heat of their furnaces and trying different sources of silica, from crushed quartz to river sand, they could alter the clarity and color of their creations. This was the dawn of systematic glass formulation. Archaeological chemist Dr. Rebecca Torres explains that by analyzing ancient glass fragments, we can see a clear pattern of experimentation. Egyptian and Mesopotamian glassmakers methodically tested different metal oxides as coloring agents. They learned that adding cobalt produced a deep, rich blue, copper could create a vibrant turquoise or even a red, and manganese could be used to remove color or create a purple hue. Each batch was a test, each artifact a data point in a centuries-long research project to understand the relationship between chemical composition and optical properties. They were not just making decorative objects, they were building a fundamental understanding of amorphous materials, substances that are not crystalline but exist in a rigid liquid-like state. This knowledge of how to control viscosity, the flow of the material when heated, was absolutely critical. Then, around the 1st century before the Common Era, a transformative innovation occurred in the Syro-Palestinian region, glassblowing. This was not merely a new craft, it was a materials processing revolution. Suddenly, artisans could take a molten gather of glass and, with their breath and simple tools, shape it into vessels of incredible thinness and complexity. This technique dramatically expanded the applications of glass, making it accessible for everyday use from containers to, eventually, windows. The principles these ancient experimenters established, the meticulous control of composition to achieve specific visual and physical properties, laid the essential groundwork for every optical advancement to come. Their mastery of viscosity and forming would one day enable the grinding of lenses, the creation of telescopes that would unlock the heavens, and the microscopes that would reveal a hidden world. The path to seeing the stars clearly began with a cookfire on a sandy beach. While Roman concrete was hardening in Mediterranean harbors and Wootz steel was being forged in Indian crucibles, a quieter but equally profound material revolution was taking shape in the kilns of ancient China. The quest was for the ultimate ceramic, a substance of pure white and resonant clarity. For centuries, Chinese artisans had perfected stoneware, but they dreamed of something more, a material that was not just strong, but also translucent and perfectly white. Their relentless experimentation between the 7th and 14th centuries would eventually produce a substance so coveted it became known as white gold. The secret lay in a specific, pristine white clay known as kaolin, combined with a feldspathic rock called Pattern-Welded. When mixed in just the right proportions and subjected to searing temperatures exceeding 1,200 degrees Celsius, these raw materials underwent a magical transformation. The body vitrified, meaning it became a fully dense, glassy solid, completely non-porous and incredibly strong. Ceramic engineer Professor Lai Wai describes this as a monumental achievement in process control. To reach and maintain such extreme temperatures consistently, Chinese kiln masters engineered massive dragon kilns, long, tunnel-like structures built up the sides of hills. The rising slope created a natural draft, pulling heat and flames through multiple chambers where artisans could carefully place their wares, each chamber offering a slightly different temperature profile. They were not just firing clay, they were conducting symphony of heat, learning to control the atmosphere within the kiln with astonishing precision. One of their most beautiful discoveries was the Celadon glaze, a soft, jade-green finish that became a signature of Chinese ceramics. This color was not achieved by adding a pigment, but through a masterful manipulation of chemistry. The potters learned to create a reduction atmosphere inside the kiln by restricting the flow of oxygen. In this smoky environment, the iron oxide in the glaze, which would normally produce a rusty brown color, was chemically reduced, creating those serene, ethereal greens. This demonstrated an advanced, albeit intuitive, understanding of oxidation states, a fundamental concept in materials science. The resulting porcelain was a triumph of engineered composition and thermal processing. It was thinner, stronger, and more resonant than any ceramic the world had ever seen. When a piece was struck, it rang with a pure, bell-like tone, a testament to its perfect vitrification. This was not merely pottery, it was a high-technology product, and it ignited a frenzy of global demand. For centuries, the Chinese guarded their formulas and techniques with intense secrecy. The specific combination of local kaolin and pattern-welded, the precise geometry of the kilns, and the exact firing schedules were state secrets, creating a monopoly that fueled a vast trade network stretching across Asia, the Middle East, and eventually Europe. Aristocrats and royalty from Venice to Versailles would pay fortunes for these exquisite white wares, viewing them as the pinnacle of refinement and luxury. The desire to unravel the mystery of porcelain would lead to centuries of industrial espionage, with European alchemists and potters desperately trying to reverse engineer the recipe. The principles of high-temperature processing, controlled kiln atmospheres, and composite ceramic bodies perfected in those ancient Chinese workshops established the very foundations of modern ceramic engineering. Today, we use these same principles to create the advanced ceramics in our smartphones, the heat-shielding tiles on space shuttles, and the biomedical implants used in modern medicine. The quest for a perfect white cup had unknowingly built the framework for materials that would one day reach for the stars. While the Chinese were perfecting their porcelain, a different kind of material miracle was emerging from the jungles of Mesoamerica. The Maya developed a blue pigment so brilliant and so enduring it seems to defy the very laws of nature. In ancient temples like Chichen Itza, vibrant murals painted over 1,000 years ago still blaze with this astonishing color, a stark contrast to the faded remnants of modern pigments nearby. This is Maya blue, and its secret was a form of ancient nanotechnology. The pigment was not a simple mixture. It was a sophisticated hybrid material created by carefully incorporating an organic dye derived from the indigo plant into the crystalline structure of a special white clay called palygorskite. Mayan artisans did not just stir these components together. They subjected the combination to a precise heating process, likely in a low-temperature fire, that permanently bonded the dye molecules within the clay's mineral lattice. Materials chemist Dr. Sofia Martinez explains this revolutionary process. The heat opened up the nanoscale channels within the palygorskite clay, allowing the indigo molecules to travel deep inside. As the material cooled, these channels tightened, trapping the dye in a protective cage. The result was a completely new substance with properties that neither component possessed on its own. The organic indigo dye, which would normally fade quickly when exposed to sunlight and water, became locked in a mineral prison, shielded from the elements that cause decay. Modern studies using X-ray diffraction and electron microscopy have revealed the stunning molecular architecture of this pigment. The indigo molecules are not just stuck to the clay, they are woven into its very framework, creating a stable composite at the molecular level. This demonstrated an early, intuitive understanding of host-guest chemistry, where one material acts as a stable scaffold for another. The Maya had discovered a way to achieve molecular stabilization centuries before the concept even had a name. The breathtaking durability of Maya blue, resisting centuries of tropical humidity, relentless sun, and even harsh chemical solvents, establishes core principles of molecular engineering that directly inspire modern science. Today, researchers look to this ancient formula for clues on how to create more stable, environmentally friendly pigments and advanced nanocomposites. How many other material secrets, born from this deep, intuitive collaboration with the natural world, are still waiting to be rediscovered in the artifacts of the past? High in the Andes, the silent testimony of Inca stonework presents a paradox that challenges our modern assumptions. Massive blocks of granite and andesite, some weighing more than 100 tons, are locked together in a seamless, three-dimensional jigsaw puzzle. The joints are so meticulously crafted that even today you cannot force the blade of a knife between them. Yet the Incas, between the 13th and 16th centuries, achieved this architectural perfection without the use of iron tools, without the wheel, and without mortar. Their secret was not brute force, but a profound, intuitive mastery of the stone itself. They understood that to shape the mountain, you first had to listen to it. The process began at the quarry, where stonemasons sought out natural fracture lines and weaknesses in the bedrock. They would carefully drill rows of small holes along a desired seam and then insert dry wooden wedges. When these wedges were soaked with water, they expanded with tremendous gradual force, cleanly splitting the stone along a precise plane. For especially hard boulders, they employed thermal shocking, building fires directly on the rock surface and then rapidly cooling it with water. The sudden thermal stress caused the outer layer to spoil off, allowing workers to then refine the shape using hand-sized river cobbles as hammerstones. This was a patient, subtractive dance with the material. Geological engineer Professor Carlos Mendez points out that the Incas were exceptional geological diagnosticians. They intuitively selected stones with specific crystalline structures that would fracture predictably, and they understood how to orient their work to exploit the stone's natural grain. They were not fighting the material's properties, they were collaborating with them. This deep material knowledge culminated in their most famous innovation, polygonal masonry. Instead of using uniform, rectangular blocks, the Incas shaped each stone into a unique, multi-faceted polygon. When assembled, these interlocking blocks created a structure that was inherently flexible. During the frequent earthquakes that shake the Andes, a rigid wall would crack and collapse, but an Inca wall dances. The stones in a polygonal wall jostle and settle against each other during a tremor, dissipating the seismic energy, and then, when the shaking stops, they simply fall back into place. This represents a revolutionary understanding of structural dynamics, an ancient form of seismic engineering that prioritized flexibility over rigid strength. The principles of material selection and shaping perfected by the Incas, their ability to work in harmony with a stone's inherent characteristics, established a legacy of resilient design. Their walls stand not as monuments to conquered nature, but as a timeless lesson in collaboration with the forces of the earth. Deep within the smoky forges of the Viking Age, another layer was being added to the story of steel. Norse smiths were pioneering a different approach to material perfection, one built not on a single uniform structure, but on a deliberate, engineered chaos of layers. They understood that the ideal sword was a paradox. It needed the hard, brittle quality of high-carbon steel to hold a razor edge, but also the soft, forgiving flexibility of low-carbon iron to absorb the shock of a brutal impact. A blade made of only one would either shatter or bend. Their brilliant solution was to combine them. Through a painstaking process, these artisans would take rods of these contrasting metals, heat them to a brilliant welding temperature, and then twist and hammer them together into a solid billet. This billet was then folded upon itself, welded again, and folded repeatedly, sometimes dozens of times. The result was a laminated composite, a material with a complex internal architecture that no single type of steel could replicate. Metallurgist Dr. Erik Johansson explains that modern analysis of these ancient blades reveals a sophisticated, if intuitive, grasp of material interactions. The Vikings were not just stacking metals, they were creating a functional gradient. The high carbon layers provided the essential cutting surface, while the softer iron layers acted as a shock absorber, dissipating energy throughout the blade and preventing catastrophic cracks from propagating. This systematic layering created a sword that was far more resilient than the sum of its parts. The distinctive patterns that swirled across the finished blade, often brought out by etching with acidic agents, were not merely for show. They were the visible map of this intricate internal laminate structure. Specific folding and twisting techniques produced specific patterns, and each pattern was more than decorative, it was functional. A certain swirl or ripple would direct stresses along particular paths within the metal, optimally distributing the forces of impact to protect the weapon's integrity. This was early stress engineering applied to metal. The development of these specific patterns represents a deep, accumulated knowledge of how material geometry influences performance. These composite metalworking techniques, perfected between the 8th and 11th centuries, established the foundational principles of laminated materials. The Viking smiths demonstrated that by intelligently combining different substances, you could create a new material that possessed a custom blend of properties, overcoming the inherent weaknesses of its individual components. This core idea, born in the fire of the forge, would echo through the centuries. It is the very same principle that guides the creation of modern composite materials, from the layered polymers in bulletproof vests that stop projectiles without breaking, to the carbon fiber composites in aircraft wings that provide immense strength with minimal weight. The legendary swords of the North were not just weapons, they were the blueprints for a material science of layered strength. Standing in the heart of Delhi for more than 1,600 years, a 7-ton iron pillar defies every expectation. While modern steel bridges require constant repainting to fight decay, this ancient monument has endured monsoons, scorching heat, and urban pollution without a trace of significant rust. This is not a mystery of lost magic, but a testament to a deeply sophisticated metallurgical science developed in ancient India between the 4th and 5th centuries. The secret lies not in a protective coating, but within the very composition of the iron itself. Recent studies using advanced spectroscopic analysis have uncovered the pillar's unique recipe. It contains an unusually high amount of phosphorus, combined with very little sulfur and manganese. This specific chemical signature points directly to the smelting techniques of the era. Ancient Indian ironmakers used high phosphorus iron ores and a particular type of charcoal in their furnaces. The process was not designed to remove impurities, but to create a specific, beneficial impurity profile within the metal. Materials corrosion specialist Dr. Anika Sharma clarifies this brilliant innovation. The traditional furnace was a bloomery where iron ore was heated with charcoal. The combustion was not hot enough to fully liquefy the iron, instead producing a spongy mass called a bloom. The craftsmen would then hammer this bloom, skillfully forging it into a solid bar. Crucially, the phosphorus from the ore and the charcoal did not burn off. It became evenly distributed throughout the iron matrix during this repeated heating and hammering process. This deliberate act created what is known as a passive layer. On the surface of the pillar, a thin, continuous film of iron hydrogen phosphate hydrate has formed, a mere fraction of a millimeter thick. This is not a layer of rust which is flaky and porous. This is a stable, glass-like barrier that adheres tightly to the underlying metal, effectively shielding it from the moisture and oxygen that would normally cause corrosion. The ancient smiths had, through masterful control of their materials and process, engineered a self-protecting metal. Modern metallurgy struggles to replicate this feat because our industrial processes are designed to remove phosphorus as an impurity, viewing it as something that makes steel brittle. The creators of the Delhi pillar understood something we overlooked, that in the right context and with the right processing, an impurity could become an asset. This represents an early, profound grasp of material-environment interactions. These artisans were not just making iron, they were designing a material to thrive in its specific conditions. The principles of corrosion resistance they established through this brilliant accident of composition continue to inform the development of modern stainless steels and protective alloys. The pillar stands as a silent, enduring lesson in working with the elements rather than simply fighting against them. That same impulse to transform humble earth into objects of luminous beauty appeared along the banks of the Nile. Egyptian faience was not mined from the earth like a gemstone. It was born from a chemical recipe. From around 4,000 years before the Common Era, artisans were engineering a synthetic material that shimmered with the sacred blues and greens of the river and the sky. They combined common ingredients, crushed quartz sand, a little lime, an alkali salt like natron, and a pinch of a copper mineral. But when these simple components were mixed, shaped, and fired, a small miracle occurred. The surface did not remain a dull, sandy paste. It transformed into a hard, bright, glossy object that seemed to capture light within itself. This was the world's first synthetic gemstone, a material created entirely by human ingenuity to mimic the rare and precious turquoise and lapis lazuli that were so difficult to obtain. The process relied on a beautiful piece of chemical engineering. In the efflorescence technique, artisans would dissolve the alkali salts in water and mix them with the quartz and copper colorant. As the shaped object dried, the water would migrate to the surface, carrying the dissolved salts and copper with it. When fired, this concentrated surface layer would melt into a brilliant, self-formed glaze. In the cementation method, the shaped quartz core was buried in a powdered mixture of the alkalis and colorants inside a sealed container. During firing, the vapors from the powder would react with the core, glazing it completely without any direct application. This was vapor phase chemistry in action, a remarkably sophisticated concept for its time. Materials scientist Dr. Nur Hassan explains that analysis of these artifacts reveals a deep, practical knowledge of material behavior. These early chemists learned to control the sintering temperature with incredible precision, keeping it just hot enough to fuse the quartz particles and activate the glaze, but not so hot that the object would warp or the color would turn black. They mastered the kiln atmosphere, understanding that an oxidizing environment would produce their beloved turquoise blues, while a reducing atmosphere could create deeper greens. This was not a single, static recipe, but a flexible system of material design. They developed different grades of faience for different purposes. A delicate, finely crafted amulet for a queen required a thin, brilliantly colored body, while a durable tile for a palace wall needed a thicker, more robust core. This demonstrated an early, clear understanding of optimizing material properties for specific applications. The creation of Egyptian faience represents a foundational moment in the history of composites, a brilliant fusion of ceramic and glassy phases into a single, entirely new substance. The principles these ancient artisans established, the deliberate manipulation of chemistry to create a synthetic material with desired aesthetic and physical properties, would resonate for millennia, influencing the development of everything from glassmaking to the advanced glass ceramics in our modern cooktops and telescope mirrors. The quest for a beautiful blue bead had quietly given birth to the very idea of engineered materials. The same mastery of materials that built eternal walls also flowed through the veins of Roman cities. While their concrete defied the sea, Roman engineers were shaping a different substance to conquer the challenge of moving water itself: lead. This soft, heavy metal became the circulatory system of urban life, chosen not out of ignorance but for its remarkable and practical properties. Roman plumbers, known as plumbarii, possessed a sophisticated understanding of lead's workability. They would cast it into large, thin sheets and then skillfully bend and shape these sheets around a wooden mandrel, expertly hammering the seam to create a perfect, watertight tube. This was not crude metal bashing, it was a precise craft of material forming. They developed specialized soldering techniques using lead-tin alloys that melted at lower temperatures, creating strong, durable joints that could withstand the constant pressure of flowing water. Materials historian Professor Marco Bellini notes that modern analysis of pipe fragments reveals an even deeper level of sophistication. The Romans did not use pure lead. They systematically alloyed it with small, deliberate amounts of tin and sometimes antimony. This was not an accident. The tin improved the lead's ductility, making it easier to form complex shapes without cracking, while the antimony added strength to the soft metal, helping the pipes better resist deformation under pressure or soil shifts. They were engineering the material's properties for its specific job. Furthermore, they understood that different water sources behaved differently. They observed that water from certain sources, particularly hard water rich in minerals, would gradually deposit a protective layer of calcium carbonate on the inside of the pipes. This scale acted as a natural barrier, isolating the water from the lead metal and effectively reducing corrosion. This demonstrated an early, practical grasp of how a material interacts with its environment, a core principle of modern materials science. The choice of lead, a metal we now know carries health risks, was a calculated trade-off based on the knowledge of the era. It represented a triumph of workability and immediate durability over long-term consequences they could not foresee. This widespread application established foundational principles of material selection for infrastructure, demanding a substance that was easily formed, readily available, and resilient against its specific service conditions. The silent, flowing legacy of those ancient pipes is not just about water delivery, but about the very idea of designing a material system to meet the complex demands of a living city. While Roman plumbers were engineering urban water systems, a completely different approach to environmental comfort was rising from the desert sands. Across the arid plains of ancient Persia, architects were turning buildings into living, breathing organisms that cooled themselves. Their most brilliant innovation was the wind catcher, a tall, chimney-like tower that reached up to capture the slightest breeze. But the true genius was not just this elegant structure, it was the specific materials they chose to bring it to life. These builders possessed a deep, intuitive understanding of thermal mass. They constructed their wind catchers and the homes beneath them from thick, dense mud bricks. During the cool desert night, these bricks would slowly release the stored cold, while during the scorching day, they would absorb heat, delaying its passage into the interior living spaces. This was not passive construction, it was active thermal regulation through material selection. Architectural engineer Dr. Farhad Nuri explains how every component was part of a coordinated system. The interiors were often finished with a special plaster made from a mix of clay, sand, and sometimes lime. This finish had specific surface properties that helped maintain comfortable humidity levels. Strategically placed within the path of the captured wind were porous ceramic water jars. As the dry desert air moved over the damp surfaces of these jars, it would undergo evaporative cooling, dropping in temperature before circulating through the rooms. This was a complete, integrated system where material, structure, and climate worked in perfect harmony, requiring no energy input beyond the wind and the careful choice of earth and water. This sophisticated knowledge of passive cooling found another remarkable application in the actual, or ice house. These ancient refrigerators were massive, dome-shaped structures built with a special heat-resistant mortar called sarouge, a mixture of sand, clay, egg whites, lime, and goat hair that provided exceptional insulation. The thick walls and the underground storage pits worked together to create a stable, cool environment where ice collected in winter or brought from nearby mountains could be preserved throughout the blazing summer months. The Persians were not just building with mud, they were manipulating the physics of heat transfer with stunning precision. They established the foundational principles of using material properties for passive environmental control, a legacy of sustainable design that directly inspires the green architects and material scientists of today. A quest for eternal life would instead unlock a force of immense power. Within the quiet gardens of Tang dynasty alchemists around the 9th century, experiments were focused on a singular spiritual goal. These seekers were not trying to build weapons, they were meticulously heating and combining minerals like saltpeter, sulfur, and charcoal, hoping to discover an elixir that would grant immortality. One fateful mixture, perhaps left too long over a furnace, did not produce a potion of long life. It flashed, it smoked, and it roared. This was the accidental birth of gunpowder, the world's first man-made explosive material. What began as a dangerous laboratory curiosity quickly evolved into a systematic field of material science. Between the 9th and 12th centuries, Chinese artisans and military engineers methodically refined these explosive formulas. They discovered that the performance was not just about the ingredients, but their precise ratios and their physical preparation. An early formula might fizzle, but a specific balance, something close to 75 parts saltpeter, 15 parts charcoal, and 10 parts sulfur, created a reliable and powerful deflagration. Chemical historian Professor Zhang Wei explains that the purification of saltpeter was the single most important technological leap. Early saltpeter, scraped from damp cellar walls, was impure. Engineers developed a sophisticated crystallization process, dissolving the crude saltpeter in water and then slowly recrystallizing it to remove contaminating salts. This yielded a far more potent oxidizer, the key to a consistent and violent reaction. They also perfected the art of grinding the components together for hours, creating an intimately mixed powder that would burn evenly and completely. This was no longer alchemy, it was precision energetic materials engineering. This systematic approach led to the world's first specialized formulations. They created a slower burning powder for spectacular fireworks, a reliable mixture for signaling rockets that could communicate across vast distances, and eventually, a much more powerful blend for the earliest projectile weapons like fire lances and bombs. This demonstrated a profound, early understanding of how to control the rate of energy release. They even grasped that the material's physical structure dictated its behavior. By moistening the powder and pressing it into cakes that were then broken into specific grain sizes, they could further control the burn rate. A fine powder was ideal for a sudden blast, while larger, denser grains provided a more sustained push, a principle absolutely critical for launching a projectile from a tube instead of simply shattering it. These experiments established the foundational principles of all energetic materials that would follow. The knowledge of how to purify, mix, and granulate a chemical mixture for a predictable and controlled release of energy would one day enable the gunpowder that reshaped global warfare, the dynamite that moved mountains for mining, and the solid rocket boosters that would eventually lift spacecraft beyond our atmosphere. The search for an elixir of life had, paradoxically, discovered how to harness the raw power of transformation itself. Deep in the humid Mesoamerican lowlands, a different kind of material revolution was taking form, one that was not forged in fire but tapped directly from living trees. The Olmec, Maya, and Aztec cultures, spanning from around 1600 years before the Common Era to the 1500s of the Common Era, were not just using natural latex. They were actively transforming it, engineering a bouncy, resilient material that represented the world's first known polymer science. Their raw material was the milky sap, or latex, from the Castilla elastica tree. In its natural state, this sap is sticky and not particularly useful, but ancient artisans made a brilliant discovery. By mixing the fresh latex with the juice of a specific vine, likely the morning glory, they triggered a chemical reaction that fundamentally changed the material's properties. The liquid sap would coagulate into a solid, elastic mass. This process, now understood through modern analysis, was a form of vulcanization, creating cross-links between the long polymer chains in the latex to make it strong, bouncy, and resistant to stickiness. This was achieved in the Americas centuries before Charles Goodyear's famous 19th century discovery. Materials scientist Dr. Javier Ortega explains that recent studies of ancient rubber balls reveal an astonishing level of control. The artisans were not making a single, standard product. They could manipulate the material's properties by varying the ratio of latex to morning glory juice. A higher proportion of juice created a harder, more solid rubber, perfect for the heavy, solid balls used in some versions of the ritual ball game. A different ratio would produce a lighter, more bouncy ball for other game types or for smaller, handheld versions. They were effectively programming the material's elasticity and density to meet specific performance requirements. This sophisticated understanding extended far beyond the ball court. The same rubber was used to create waterproof coatings for textiles and containers, and evidence suggests it was even used to make durable, rubber-soled sandals. This demonstrates a clear grasp of material applications, tailoring the same base substance for wildly different uses, from ceremonial sport to practical, everyday waterproofing. These ancient techniques established the foundational principles of polymer modification. The Mesoamerican discovery that you could chemically alter a natural polymer to create a new material with custom-engineered properties is a core concept that drives our entire modern rubber and plastics industry. Every car tire, every bouncy ball, every waterproof jacket owes a conceptual debt to those early innovators who looked at a dripping tree and saw the potential for a substance that could defy its own nature. Along the fertile banks of the Nile, a different kind of engineering was taking root. While the Egyptians were masters of stone and faience, they also perfected a technology of information, transforming a simple marsh plant into a medium for eternity. The papyrus reed was not merely cut and used, it was systematically processed into the world's first engineered writing surface. This was not a casual craft, but a sophisticated material science that understood plant fibers on an intimate level. Harvesting occurred at a precise time in the plant's growth cycle to ensure the stalks had the ideal balance of strength and flexibility. Craftsmen would then carefully slice the pith of the triangular stalk into thin, uniform strips. The true genius, however, lay in the assembly. These strips were arranged in two perpendicular layers, one horizontal and one vertical, then soaked in the Nile's water and hammered together. Under pressure, the plant's own starchy sap acted as a powerful, natural adhesive, bonding the layers into a single, cohesive sheet. Paper conservation specialist Dr. Amina Khalil explains that this cross-lamination was the key to its legendary durability. By orienting the fibers in opposing directions, the Egyptians created a composite material that resisted tearing and cracking from any single direction of stress. This was an ancient precursor to modern plywood or carbon fiber, where the strength comes from the layered, multidirectional alignment of the components. The process did not end there. The sheets were then pressed, polished with smooth stones or ivory to create a perfect writing surface, and finally joined side by side to form long scrolls. This was a full-scale manufacturing process with a clear understanding of quality control. They developed different grades of papyrus, from the finest, smoothest sheets reserved for religious texts and royal decrees, to coarser, more affordable versions for everyday administrative records and personal letters. This grading system demonstrates an early, formalized understanding of material standards, ensuring the right product for the right application. The principles of fiber separation, cross-lamination, and natural adhesion established along the Nile would echo through the centuries. While the specific recipe for papyrus was eventually lost, the core concepts of manipulating plant fibers to create a uniform sheet would later inspire the papermakers of China and the Islamic world, and ultimately lead to the paper we use today. The desire to record a thought permanently had driven the invention of a composite material that could outlast empires. Deep in the darkened galleries of Roman mines in Spain and Britain, the quest for silver drove a revolution in chemical processing. The miners faced a complex material puzzle. Silver was rarely found in its pure form, but was intricately locked within a lead ore called galena. To free it, Roman metallurgists perfected a brilliant two-stage sequence that demonstrated a masterful grasp of material separation. The first step was smelting. They would crush the ore and roast it in a furnace, driving off the sulfur and leaving behind a molten mixture of lead and silver. This liquid metal was then poured into a special furnace called a cupel, a shallow hearth lined with bone ash or crushed seashells. As air was blown across the surface of the molten metal, a controlled miracle of oxidation occurred. The lead, being far more reactive, eagerly combined with the oxygen, transforming into a liquid oxide called litharge. This litharge was either absorbed into the porous cupel lining or skimmed off the surface. What remained in the hearth was a gleaming button of nearly pure silver. This cupellation process was not a simple heating. It was a precise chemical separation reliant on a deep, intuitive understanding of how different materials behave under extreme thermal stress. Mining archaeologist Professor Thomas Reed explains that the efficiency of these operations reveals a systematic, almost industrial approach. Roman smelters did not use a single, universal method. They experimented constantly with furnace designs, airflow, and the use of additives called fluxes. For different types of ores, they would test different mineral fluxes to help separate the valuable metal from the rocky waste, or gangue. They were running large-scale optimization experiments, mapping out which combinations of heat, air, and chemistry would yield the highest return of precious metal from a given batch of rock. This relentless, practical research established the foundational principles of extractive metallurgy. The knowledge of how to isolate a desired substance from a complex mixture through systematic processing became a cornerstone of material science. The techniques refined in those smoky, silver-hungry furnaces, the understanding of oxidation, the use of fluxes, and the design of separation processes would provide the essential toolkit for every metallurgical advance to come. This was the quiet, gritty beginning of chemical engineering, born not in a clean laboratory, but in the soot and fire of the ancient world, setting the stage for all future efforts to purify and transform the materials of the earth. High above the ancient mines of Zawar in India, a different kind of alchemy was taking shape. While Roman smiths wrestled with lead and silver, Indian metallurgists confronted a far more elusive metal, one that seemed to vanish into thin air. Zinc presented a unique and maddening challenge. Unlike copper or iron, it does not melt and pool conveniently at the temperatures achievable in a traditional furnace. Instead, it vaporizes, transforming from a solid ore directly into an invisible gas around 900 degrees Celsius. To capture this volatile spirit required not just heat, but a revolution in containment. Their brilliant solution, emerging around the 12th century, was a sophisticated distillation process that feels eerily modern. They crafted special clay retorts, sealed ceramic vessels that acted like miniature chemical reactors. Inside, they placed a precise mixture of zinc ore and charcoal. When the retort was heated in a furnace, the chemical reaction began, producing zinc vapor. But the true innovation was the design of the condenser. The retort was fitted with a long, downward-sloping tube that extended into a water-filled pot. As the invisible zinc gas traveled down this cooled passage, it would condense back into a liquid and then solidify into pure metallic zinc. This downward distillation was the key, a deliberate design that used gravity to guide the vapor away from the heat and into a zone of controlled cooling. Materials historian Dr. Rajiv Mehta points out that the archaeological remains at Zawar are not just ruins, they are a preserved laboratory. The site reveals an almost industrial-scale operation, with thousands of these retorts used in coordinated batches. The metallurgists had mastered a critical balance, maintaining a temperature high enough to produce the vapor, but within a narrow range that prevented the fragile clay retorts from cracking under the stress. This was not a haphazard process. It was a systematic, repeatable technology for mass-producing a pure, volatile metal. This deep understanding of material volatility allowed for another significant achievement, the reliable production of brass. Before this, brass was made through a laborious cementation process where copper was heated with zinc ore and charcoal, hoping some zinc would diffuse into the copper. Now, for the first time, artisans could directly alloy precise amounts of pure, distilled zinc with molten copper. This demonstrated a profound grasp of how to combine metals with vastly different physical properties, one stable and molten, the other volatile and gaseous, to engineer a new, golden-colored alloy with its own unique set of qualities. The principles of gas-solid transformation and condensation captured in those ancient Indian retorts established a foundational chapter in the story of metallurgy. They were working with the very nature of the elements, not against them, and in doing so, they built a technological bridge to methods that would define modern industry centuries later. Aboard a Byzantine warship, a terrifying new weapon roared to life. It was a liquid flame that clung to the sea itself, a fire that water could not quench. This was Greek fire, and for over 5 centuries it was the ultimate guardian of Constantinople, a technological secret so potent it shaped the destiny of an empire. Historical accounts from besieged enemies describe a horrifying spectacle, a jet of liquid fire launched from bronze tubes mounted on the prows of ships, igniting enemy vessels into unstoppable infernals. The psychological impact was as devastating as the physical damage, creating a wall of flame that defended the city's seawalls time and again. Behind this weapon lay a profound mastery of materials, a systematic program of chemical experimentation conducted between the 7th and 13th centuries. Researchers were not just throwing ingredients together, they were running rigorous tests on petroleum-based naphtha, experimenting with various additives to control its burn rate, viscosity, and ignition. Chemical engineer Professor Dimitrios Papadopoulos explains that the true genius of Greek fire was not just in its secret formula, but in its entire delivery system. The Byzantines had to solve immense practical challenges, developing pressurized bronze siphons with pumps and heated tanks to eject the volatile mixture. They understood that the material had to be precisely the right consistency to be projected in a steady stream, yet still ignite upon contact with the air or water. This required an advanced, if intuitive, grasp of fluid dynamics and combustion science. Modern reconstructions suggest a complex cocktail likely involving crude naphtha mixed with resins to make it sticky, and possibly quicklime, a substance that heats up violently when it contacts water, ensuring ignition even on the waves. The empire guarded this material science with obsessive secrecy. The knowledge was confined to a single family, and the penalty for revealing the formula was death. This demonstrates one of the earliest examples of understanding that advanced material processing was not just a craft, but a strategic advantage of state. The principles of chemical incendiaries and their specialized delivery mechanisms, perfected in those Byzantine workshops, established a foundational blueprint for energetic materials. It was a stark lesson in how the control of a single substance's properties could alter the balance of power for centuries, proving that the most powerful secrets are often those we learn to wield from the earth itself. A platinum bead from ancient Peru presents a material science paradox. This metal stubbornly refuses to melt until it reaches a temperature of over 3,200 degrees Fahrenheit, a heat far beyond the reach of any pre-Columbian furnace. Yet there it is, a polished, durable artifact crafted between 100 years before the Common Era and 700 of the Common Era. How did these master metalworkers conquer a material whose fundamental property seemed completely out of their reach? Their solution was not to fight the impossible melting point, but to invent an entirely different pathway. They bypassed the liquid state altogether, pioneering a brilliant technique we now call powder metallurgy. Along the coast of what is now Ecuador, artisans would patiently gather tiny, granular grains of platinum from alluvial deposits in rivers. These naturally occurring platinum particles became their raw material. They would then mix these minute platinum grains with a small amount of gold dust and a liquid metal, mercury, to create a pliable, clay-like amalgam. This malleable paste could be shaped into beads, rings, or small ornaments, but the true transformation happened next in the fire. When the object was heated, the mercury would slowly vaporize and drive off, leaving behind a consolidated mass. The heat was not nearly enough to melt the platinum, but it was sufficient to cause the surfaces of the individual platinum and gold particles to slowly bond together at their contact points, a process known as sintering. The gold acted as a kind of metallic glue, filling the spaces between the platinum grains and helping to form a solid, cohesive object. Once the mercury was gone and the sintering was complete, the artisan would then subject the object to intense, repeated hammering. This mechanical working further compressed the structure, closed any remaining pores, and work hardened the metal, giving it a satisfying heft and a beautiful, polished luster. Materials archaeologist Dr. Isabella Fernandez explains that recent analysis of these artifacts using scanning electron microscopes reveals an incredibly sophisticated microstructure. The ancient metalworkers had achieved a near-perfect sintered bond, creating a composite material that was both dense and strong. They were not just making shapes, they were manipulating matter on a granular level, understanding how to make solid particles coalesce into a unified whole through the careful application of heat and pressure. This was a profound leap in material processing. These artisans demonstrated that you could engineer an object from the bottom up, starting with a powder and building it into a solid form. This principle of solid-state processing, where materials are transformed without ever being melted, is a cornerstone of modern manufacturing. The very same concept drives the creation of tungsten carbide cutting tools, the fabrication of specialized magnets, and even the 3D printing of metal parts in additive manufacturing. Each of those platinum beads is a silent testament to a lost school of engineering, a reminder that the path to material mastery is not always a straight line, but often a brilliant, creative detour around an impossible obstacle. While Roman plumbers shaped lead and Byzantine engineers unleashed liquid fire, a different kind of industrial revolution was quietly taking root in the heart of ancient China. By the 5th century before the Common Era, Chinese ironmasters were not merely forging weapons, they were orchestrating a symphony of fire, earth, and metal on a scale the world had never seen. Their workshops hummed with the roar of massive blast furnaces, structures towering over workers, designed to funnel a continuous draft of air to achieve temperatures that could liquefy iron ore completely. This was the dawn of true cast iron production, a technological leap that transformed iron from a precious, laboriously worked material into a commodity that could be mass-produced for an entire civilization. The secret to this industrial scale was a combination of brilliant furnace design and a strategic fuel choice. While other cultures relied on charcoal, Chinese innovators systematically utilized coal, a far more abundant resource that burned hotter and could sustain the immense, continuous heat required to keep iron in a liquid state. This shift from batch processing to continuous production was as revolutionary as any assembly line. The molten iron could be tapped directly from the furnace and poured into vast arrays of prepared clay molds, producing dozens of identical plowshares, cooking pots, or axle hubs in a single casting. This was not just crafting, it was manufacturing. Metallurgical historian Professor Wang Jian explains that these early masters did not see cast iron as a single, fixed material. Through meticulous observation, they learned to engineer its very microstructure by controlling how it cooled. If the molten iron was cooled rapidly, it solidified into what is known as white cast iron, a material incredibly hard and wear-resistant, perfect for the cutting edges of plows that had to scrape through rocky soil. But this hardness came with brittleness, so the ironmakers developed a solution, a revolutionary heat treatment known as annealing. They would take a cast white iron object and bury it in an oxidizing material like iron ore, then heat it for days on end. During this slow, controlled process, the carbon within the brittle iron would gradually diffuse out, transforming it into malleable cast iron, a material that was still strong but now much tougher and able to withstand impact without shattering. This ability to custom tailor the properties of iron for specific applications, from a farmer's tool to a carpenter's plane, represents a profound grasp of materials engineering. The ultimate expression of this mastery stands in the iron pagoda of Yuquan Temple, a structure cast in the 11th century. Its thousands of interlocking components, each perfectly molded and fitted, speak to an unbelievable command of mold design and an intuitive understanding of metal fluidity. The artisans knew exactly how to channel the molten iron through intricate gating systems to fill every detail of the complex molds, ensuring thin walls and precise features would cast perfectly. This was mass production with artistic precision, establishing the core principles of standardization and interchangeable parts that would one day fuel the industrial age. The quiet, systematic work in those ancient Chinese foundries had unknowingly built the conceptual framework for the modern world. Across the African continent, a different kind of alchemy was unfolding in the heat of the bloomery furnace. From the highlands of Tanzania to the forests of Nigeria, ironmakers between the 5th and 18th centuries were not just smelting metal, they were conducting a symphony of earth, air, and fire to produce steel of remarkable quality. Their furnaces were masterpieces of design, tall, cylindrical structures often built with sophisticated internal chambers and tires, the pipes that directed air. These were not simple holes for bellows, they were precisely angled to create specific swirling airflow patterns, controlling the furnace atmosphere with an artisan's touch. The choice of ore was a science in itself. These metallurgists would seek out specific iron sands or lateritic ores known to contain just the right trace elements. They paired these ores with charcoal made from particular types of hardwoods, understanding that the wood's density and chemical makeup would influence the carbon content of the final metal. Through this meticulous control, they could consistently produce a bloom of steel, a spongy mass of iron-carbon alloy, directly from a single, masterfully managed operation. Anthropologist Dr. Kwame Adebayo explains that this profound technical knowledge was woven into the very fabric of cultural life. The entire process, from mining the ore to the final smelt, was often guided by ritual and oral tradition. Certain trees were chosen for charcoal not only for their burning properties but for their spiritual significance. Songs, incantations, and ceremonial practices were not separate from the science. They were the vessels that carried the precise, accumulated knowledge of generations. These rituals encoded critical information about timing, temperature, and material selection, ensuring that the complex, multi-step process was repeated with flawless accuracy long before the advent of written manuals. The resulting steel was then expertly worked into objects that served every dimension of life. A farmer's hoe blade was forged to have a resilient toughness, able to withstand rocky soil. A warrior's sword required a harder, sharper edge that could hold its keenness in battle. And ceremonial objects like staffs or ritual blades embodied both physical perfection and deep cultural meaning, their creation a testament to a society that viewed material properties and spiritual significance as inseparable. These African metallurgical traditions represent a unique and highly advanced branch of materials engineering, one that understood the process as a holistic integration of environment, knowledge, and culture. The principles they established of systematic ore selection and atmospheric control within the furnace continue to offer valuable insights for modern scientists studying sustainable material processing and the rich, untapped potential of indigenous knowledge systems. A clear pattern emerges from these ancient laboratories of fire and earth. Our ancestors were not merely lucky discoverers, but systematic experimenters who built the very foundations of modern engineering. From the self-healing Roman concrete in Mediterranean harbors to the molecular cage of Maya blue that resists fading after 10 centuries, these were not accidents. They represent a sophisticated, intuitive grasp of material behavior that we are still struggling to fully decode with our most powerful microscopes and analytical tools. This was a legacy of relentless testing, of trying different compositions, varying processing methods, and carefully observing the results across countless generations. The principles they established through this cumulative process, the understanding of alloying, heat treatment, composite design, and microstructure control, are the very same principles that enable our modern world. They are the reason we can build soaring skyscrapers, create spacecraft that survive re-entry, and develop the advanced composites in everything from athletic equipment to medical devices. This long arc of progress reveals a profound truth. Engineering breakthroughs rarely arrive as sudden, isolated revelations. They are almost always the product of gradual, collective experimentation, where each generation stands on the material wisdom of those who came before. As we now confront our own monumental material challenges, from creating sustainable building products to developing ceramics for interstellar travel, we might find that some of the most elegant solutions are not waiting in the future, but are quietly embedded in the past. The next time your eyes trace the lines of an ancient pottery shard, or you stand in the shadow of a 1,000-year-old temple, remember that you are witnessing more than just history. You are looking at the enduring results of sophisticated material experiments that continue, even now, to shape our engineered world.